Hello, this is my Module 3 for Rebecca Butler. Starting with my MRC by hand calculations, as well as my ANOVA by hand calculations. All right, and I'm going to start sharing my screen and get started with the module. All right. Okay. All right, so I was given data from a client and was told to run an ANOVA on it and then give them the results. ANOVA is a method that comes from the general linear model and analyzes variances to determine the statistical significance of differences between means. So I took a look at the data they had collected, and I just couldn't in good consciousness just run one line of code and then give it to them to interpret on its own. To give you a quick idea of what the data they gave me was, they were trying to predict success of students with learning disabilities in high school from the two factors of one, whether the child was in self-contained classes, and the two, whether the child was given extra time on tests. The factor of self-contained classes had two levels, yes or no, 1 and 0. And then the extra time on tests had 3 levels, no extra time, an extra 1 times the original amount, so double, or an extra 2 times the original amount, so triple, and those were and 2. I ran the ANOVA, which also included the interaction between our two predictors. That extra time on tests was a significant predictor at the 0.05 level. However, before we take this just at face value, I had to look at some of the assumptions of ANOVA. We did verify that the errors were IID normal, or independent, identically distributed, and distributed normally. And as you can see, we failed to reject the null on these tests of homogeneity of variance for the two factors, so for both of them. So we can say to some certainty that the variance for each group is the same. So that was good. But something else that really stuck out to me, and this is probably the easiest violation to detect by just looking at the observations, is that the data isn't balanced. Ideally, this should all be the same number, these 6 cells here. Observations, which is what they had, we should have 5 of each combination. So 0, 1, and 2 represents the extra time on test, and 0 and 1 is self-contained classes, and we should have 5 observations of each one of those combinations. And ANOVA is really sensitive to unbalanced designs, so this was a red flag for me. Using an unbalanced design doesn't completely render the results of an ANOVA useless, but it does mean you have to interpret the data with caution and with that in mind. So rather than continuing to test other assumptions, I explained to my client that using MRC and multiple regression might be a better idea for the data that they've collected. We're still focused on variability, but the analysis isn't as sensitive to violations of balance or the assumption of homogeneity of variances, even though that wasn't an issue here. The thing that really sold me on the switch to MRC was when they started discussing another variable they had collected that they hadn't mentioned before, working memory, which is a continuous variable. Now, ANOVA needs categorical variables like the ones we were already using, but the MRC can use either categorical or continuous variables. You can split a continuous variable into groups for ANOVA, but this drastically decreases the statistical power, so it's really not a good idea. So ultimately, my client gave me the data on the working memory and the okay to switch from ANOVA to MRC, and these were the data that we had. Before we dive too far into the MRC model, I want to explain a few similarities and differences between ANOVA and MRC. As I've said, both models are part of the general linear model, so they both assume an additive relationship between X and Y, as you see here in this formula. As part of the GLM, ANOVA and MRC both have similar assumptions that we must look at to determine if the results we're getting are defensible. However, philosophically, while both models acknowledge that there are imperfections in the world, ANOVA assumes the imperfections are in the observations, whereas MRC asserts that the imperfections are in the model itself. And when I mean imperfections, I'm talking about this E, as it's known in ANOVA, or residuals for MRC. Okay, so let's run a regression model on our 3 covariates now. We've added working memory, the model, and we're keeping the interaction between self-contained classes and extended test time. And something I want to just point out is that the dependent variable of success is a continuous variable, not a dichotomous one like pass or fail with only 2 options. Cortina 2002 reiterates how dichotomous dependent variables are inappropriate to use with MRC. And they mess with the normal distribution of errors and the variance and should just be avoided. So just want to be clear on that, that this is a continuous measurement of success, not just a strict pass or fail. Right, so looking at our results again, when we run the model, we see that extended time on test is again significant at the 05 level, but now so is working memory. And honestly, if I was writing up these results, I would present the p-values for all of these variables because, as Gary King pointed out, it's best to give people all the information and let them come to their own conclusions. Even though neither of the other p-values are close to 0.05, omitting that information when you're reporting it leaves people to wonder whether those values could have been something like 0.055 or something that they, in their interpretation, may still be significant for whatever they're trying to interpret the data for. But for us, we'll just consider both of these 2 variables already mentioned are statistically significant predictors of success for students with learning disabilities at a 0.05 level. So we see from our coefficients up here that an increase in working memory increases the success value, but doubling or tripling the time on tests decreases success according to this model. But before we get ahead of ourselves, let's look to see if any of the assumptions of the MRC were violated and need to be taken into consideration. All right, so first, always plot your data. From plotting the data, we have no reason to think that the relationship between any of the x's and y is not linear. Secondly, the predictors we're using are sensible, so that's good. However, there may be other predictors not included in this model that are relevant for predicting success for students with learning disabilities, and that is something that we should worry about. You can see if we go back to our MRC model that the 3 predictors and the interaction account for about 45% of the variance, and we can tell that from our R-squared value. So there may be other variables we could measure to help account for more of that variance and better predict our Y value. All right. So we are assuming no measurement error, even though that one's a little difficult to take 100% seriously. We are assuming that the only error is random. The mean error equals 0, so we see that here. This is very, very close to 0. That's good. Then we evaluate the residuals versus fitted graph to check for homoscedasticity, and we see that this line here is mostly above 0 and then dips down right here. So the variance isn't exactly constant. If it were, it would be right along this line, the 0 line. We want to keep in mind that there could be some heteroscedasticity in the data. Then looking at our QQ plot, we see that the residuals aren't perfectly normal either. If they were, they'd be right along this dotted line here, bounce back and forth a little bit, and there could possibly be some outliers. And that's another thing that we do want to check is any potential outliers. So we saw a couple of those observations that were labeled as potential outliers. But we look at this graph here, and although some points do have a higher leverage, none of the points are outside of Cook's distance, which is marked on these by these dotted red lines. Cook's distance measures the amount of influence a single observation has on the results. So we see that none of them are outside of the limits that we've set, so we're fine without any real outliers that we need to consider. Then we must check for multicollinearity. Just looking at the correlation matrix, we see that working memory and time on tests are negatively correlated. We also see, this isn't related necessarily to multicollinearity, but we also see that working memory and time on tests are correlated with our Y, and that makes sense since those were both found to be significant when we were looking at the results earlier. But this correlation here between our predictors is a concern. Then when we look at our variance inflation factors, we see that the VIF for self-contained classes and the interaction between self-contained classes and time on tests is over 5, and that's huge for a VIF. Lowers the precision for the estimated regression coefficients and generally increases the likelihood of a type 2 error. Even though we've rejected the null for 2 of our variables, the multicollinearity in the data means that we could be committing a type 2 error by failing to reject the null on one of the other predictors as well. So ultimately, what I can tell my client is that based on the data they provided, time on test and working memory are significant predictors of the success of students in high school. However, I would caution them that with that interpretation because of the broken assumptions and the multicollinearity in the data. So with that, thank you.